Jai Hind to all. My name is Dr. Divya Sharma, Assistant Professor in Akgec Engineering College, Ghaziabad. Now, today's video lecture is on DC analysis of operational amplifier. This topic is taken from integrated circuit. Its code is BEC 501. So, here in this presentation, we will do DC analysis of 741 operational amplifier circuit, in which we have to do DC analysis of input stage, second stage, output stage, and reference bias circuit is there because biasing current is provided to input stage from reference bias circuit. So, this is the internal structure of 741 IC. Here transistor, resistor, capacitors are present in this internal structure of 741 IC. Now here there are first stage, this one is first stage, second stage, output stage, and here is a reference current circuit. Now for the input stage, how many transistors are there for input stage? Transistor Q1, Q2, Q3, Q4, Q5, Q6, Q7. So Q1 to Q7 transistors are present in input stage. Now in the second stage, Q16 and Q17, these two transistors are present in second stage, and biasing current is provided to this second stage is from Q13B, and this output of the first stage, and this first stage biasing current is provided to this first stage is from this point X and this point, and this and the next one is output stage. Output stage transistors are Q14 and Q20. Now these two transistor bias current is provided from this Q13A and this one. This is these transistor Q15, Q21, Q24 and Q22. These transistors are for short circuitry transistors. Now why we are connecting here short circuitry transistors here? To protect the circuit. For large means for shorting, means to provide sorting for the circuit diagram by using this short circuitry protective circuit. Now here, so output is provided at this stage, and this is a reference current circuit where transistors Q11 and Q12 are present. So bias current is provided to this input stage from this reference current stage. Now one more thing I want to tell you, that there are two transistors Q13A and Q13B. So collector current of these two transistors are in parallel and in proportion. Here is 0.75 and here is 0.25. And area of the output stage means output transistors are Q14 and Q20. Its area is 3 times of the standard operational amplifier. Of the standard transistor, sorry. So if its area is more, it means transistor's width is more, and transistor width is more, it means large current is provided to this output stage. So this is the internal structure for this operational amplifier. Now we will start with the DC analysis of this input stage, second stage and output stage for this operational amplifier. Now first we will start with the reference bias circuit. So this is the circuit diagram where you have transistor Q11 and Q12. So, and these two are two diode connected transistors are there, Q11 and Q12. Now here we have to find out I reference current, which is provided to the Widlar current source, means next circuit diagram, and which is connected to the input stage. So first we have to find out I reference. Now this is the circuit diagram. We have to apply here KVL. When we are applying here KVL, you can see this is this emitter of this Q12 is connected to VCC, and here is ground. So this one is VCC and ground. VCC is plus 15 volt and minus VE minus 15 volt. Now apply here KVL. When we are applying KVL in this circuit diagram, you will get equation VCC minus VBE 12 minus I reference into R5. This is the R5 resistor is connected to this. Now minus VBE 11. So voltage VBE across this transistor Q11 minus VE. So this is the, when we are applying KVL, this is the equation. Now here we have to find out I reference. I reference is VCC minus VEB transistor 12 minus VBE transistor 11 minus VEE upon R5. Now you know the value of VCC and VE is 15 volt, and here VBE 12 and VEB 12, sorry, VBE 12 and VBE 11 is equal to 0.7 volt. So now consider these values and put all these values in this equation, and you will get the reference current that is equal to 0.73 milliampere. So it will help you in the next circuit diagram. That's why we are calculating I reference, that is equal to 0.73 milliampere. Now this is the circuit diagram. This is the circuit of Widlar current source. Now you can see the internal structure. This is your reference current circuit, and this is your Widlar current source. Here this is Widlar current source circuit. Here I reference is calculated from this reference current bias circuit, and we have to calculate here current at this collector terminal of this Q10. So we have to calculate here. So first we are considering this circuit diagram, and we have to calculate voltage, means current at this point. Why we now here, what is main point is that we have to find out current and voltages at all the terminals of each transistor in this internal structure of operational amplifier. That's why first we are calculating I reference, then we have to calculate here IC10. So when we calculate IC10, so it will provide biasing current to this input stage. Now this is the circuit diagram of Widlar current source. Here I reference already calculated in the previous slide. Now this is transistor, two transistors are connected here, Q10 and Q11. So here we have to calculate IC10. Now Q11 is biased by I reference, and voltage developed across it is used to bias Q10, which has a series emitter resistance R4. Right? Now assume beta is very large. It means you can consider here base current is nearly equal to 0. Now apply KVL across this circuit diagram. So here minus VEE, here is also minus VEE. Now apply KVL across this circuit diagram. So write down the equation minus VEE, here is minus plus minus plus minus. So when we are moving in the direction of current, if we are considering minus VE, it means minus, this one is also minus, and this one is plus, and this one is plus, and this one is, this term is plus. So when we are applying KVL, minus VEE, if we are considering minus VEE minus, so this is also minus. So minus VE minus VBE, voltage drop across this transistor Q11, plus VEB, this is voltage across this transistor 10, plus IC10. Now here if we are considering IB is nearly equal to 0, it means IC10 is equal to IE10. So here we can replace IE10 is equal to IC10 R4 plus minus VEE is equal to 0. Now we know the value of VEE and V, so you can see this equation, and this one is cancel out. So now we will get this equation VB11 minus VB10 is equal to IC10 R4. Now we know that collector current equation is this, IC is equal to IS e ki power VBE upon VT. Now here this is collector current, this is saturation current, exponential VBE upon threshold voltage VT. So you can say this is the relation between IC and VB. Now by using this equation, we can find out, from this equation we can find out VBE. VBE is how much? VBE is equal to VT ln IC upon IS. Now this is the standard equation, VBE. Now can you find out VBE for this transistor 11 and 12? So we can find out VBE 11 is equal to VT ln IC, means collector current for this transistor 11 is I reference. I reference is the collector current for transistor 11. So put here I reference upon saturation current for transistor 11. Now calculate VBE 10. VBE 10, put here the value for VBE 10 is equal to VT ln. Now collector current for this VBE 10 means collector current for this transistor Q10 is IC10. So put here collector current is equal to IC10 upon IS10. Now assuming saturation current for this transistor 11 and 12 are equal. So put this IS11 and IS10 both are same, means we are assuming both are equal. So put this equation in this equation and this one. So you will get VT, when you will put IS11 here and IS10 means both are equal. So you will get VB11 and VB10 and put these two values in this equation 1. So you will get this equation VT ln I reference upon IC10 is equal to IC10 R4. Now here this is the final equation. From this equation we can find out IC10 and we know the value of VT. VT is how much? 25 millivolt. I reference already calculated in the previous slide, that is equal to 0.73 milliampere, and R4 it is given in the circuit diagram, that is equal to 5 kilo ohm. So this value is given in the internal structure of operational amplifier. So put all these values in this equation and by trial and error method we can find out IC10 is equal to 19 microampere. So this is the DC analysis, means we are calculating terminal currents for this transistor 11 and 10. So these means IC current we are providing here, we are getting here IC10, that is 19 microampere, which will help in biasing. This is the biasing current to the input stage. Now we will start with the input stage. So in input stage here Q1, Q2, Q3, Q4, Q5, Q6 means Q1 to Q7 transistors are there in the input stage. So this is the half circuit diagram. First we are calculating terminal currents across this transistor Q1, Q2, Q3, Q4. Now here we are getting here IC10 in the previous slide. Okay. Now here let us consider here 2I current is there, 2I, and now these two transistors are identical you can see these two transistors are identical transistors. So if let us assume here 2I current is there in this input of this circuit diagram, so it is divided in transistor Q1 and Q2 is equal in proportion, this is I and this is I, right. Now base current is here equal to 0. If base current is equal to 0 for this transistor Q1 and Q2, so IC current of this transistor Q1 and Q2 is equal to I current of transistor Q1 and Q2. So here is also current I. Now here we are assuming this base current is also nearly equal to 0. So here also I current is flowing in this collector current of transistor Q3 and Q4. Now here you can see from the symmetry of Q1 and Q2, IC1 is equal to IC2 is equal to I, and I3 is equal to I4 is equal to I, and Q3, Q4 transistors are also equal. So you can see IB3 is equal to IB4. You all know we are assuming here base current is nearly equal to 0, but actually IB is equal to how much? IB is equal to IC upon beta. If beta is very large, then we can consider IB is equal to 0. But here we are considering IB3 is equal to IB4 is equal to IC upon beta, and IC is how much? IC is equal to I. So this is the equation. Now consider current mirror found by Q8 and Q9. Now Q8 and Q9 are current mirror. Now current is provided this terminal of Q19 by using this current mirror equation. We will get here 2I upon 1 plus 2 upon beta. Now here we have to find out IC10 is how much? IC10, when we are applying KCL at this point, let us consider this is point X. So IC10 is equal to 2i. How we will get IC10 is equal to 2i? Now you can see at this point, at node 10, IC10 is equal to 2i upon 1 plus 2 upon beta plus 2i upon beta. If we are considering beta is very, very large, so this will become 0 and this will become 0. So we will get here IC10 is equal to 2i. And you know the value of IC10 from the previous slide. It is already calculated. IC10 is equal to 19 microampere. So we can find out I is equal to IC10 upon 2. So I is equal to 9.5 microampere. So this is calculated. Now IC1, IC2, IC3, IC4 equal to I, that is equal to 9.5 microampere. So this is the half input stage circuit diagram. Now the further in the next slide, here transistor Q5, Q6, Q7. So because we have to find out current all the terminals in each transistor, so now here we have to find out, already it was discussed in the previous slide that IC6 is equal to I and IC4 transistor 5 is equal to I. Now here we have to find out current. Here is also, if base current is assuming, we are assuming here 0 and here also we are assuming 0. It means here is also IE for this transistor Q5 and IE for transistor Q6 is also equal to I. So here we have to find out current across this terminal. So for this we have to find out IC3 dash. IC3 dash, we have to apply here KVL. Now when we are applying KVL at this in this circuit diagram, so minus, you can see this equation, when we are applying KVL, minus V minus I3 dash R3. Now here this is plus, this is minus, this is equal to plus V. If we are moving in the current direction and we are considering that here is minus, this one is minus to plus, if it is considering minus, so plus to minus is plus. So here plus VB6 plus IE6, and IE6 is how much? IE6 is equal to IC6 is equal to I. Minus V is equal to 0. So this one is cancelled out and we will get IE6 equal to IC6 if IB is equal to 0. So you can put here IE6 is equal to IC6. So from this equation we will get I3 dash is equal to VB6 plus IC6 R2 upon R3. Now put this equation 2 in this equation 1. Now you can see this equation, this is IE, here is IE7 is equal to how much? 2, this I plus I upon beta plus I upon beta. If we are applying KCL at this point, so IE7 is equal to I upon beta plus I upon beta plus I3 dash. So this one we have to calculate. This is equation IC7 is equal to IE7 is equal to 2I upon beta plus I3 dash. That's why we have to calculate I3 dash. This is unknown value. So this one we have to calculate. This is IE3 dash. So this equation, put in this equation 1, we will get IC7 is equal to IE7 is equal to 2I upon beta n plus this is your I3 dash. And here if beta is very, very large, it means 2I upon beta is equal to 0. So IC7 is how much? IC7 is VBE6 plus IC6 R2 upon R3. Now put here this VBE6 is 71517 milliampere. Here it is calculated. VBE6 is here. VBE6 is how much? VT ln IC6 upon IS. And you know the value of VT. You know the value of IC4 is equal to IC6 is equal to 9.5 microampere and our saturation current is 10 to the power minus 14 ampere for NPN transistor. Now put here these values and we will get VBE6 is equal to 517 milliampere. So this value you can put here and IC6, you know this is 9.5 microampere. R2 value is given in this circuit diagram, that is 1 kilo ohm. So put all these values and I3 is 50 kilo ohm. So put all these values in this equation IC7 and you will get IC7 is equal to 10.5 microampere. Now this is the second stage. Now in the second stage you can see these two transistors are in second stage, Q16 and Q17. Now biasing current is provided in the second stage from Q13B, and Q13B is the proportion 0.75, and this transistor connected to Q12, and Q12 current is flowing across this Q12 transistor is how much? I reference 0.73 milliampere. Now IC13B is equal to 0.75 I reference. So you can put here the value of I reference and you will get IC13B, or you can say collector current of this transistor Q17 is how much? 550 microampere. Now here also we should know the value for this current flowing across this emitter terminal of this transistor Q16. So this is unknown value, we have to find out I9 dash. So before we have to find out this, you should know VEB17. VB17 we can calculate VT ln IC upon IS, and for this transistor IC is IC17, and already it is calculated here 550 microampere. Put here the value of IC saturation current for this transistor Q17, that is equal to 10 to the minus 14. VT is already we know that is 25 millivolt. So put all these values in this equation and find out VB17 is equal to 618 millivolt. Now we will get this one. Now here we have to find out I9 dash. Apply KVL at this in the circuit diagram. So if we are applying KVL, this is minus VEE and this one is also minus VE. So when we are applying here KVL, so we will get minus VE minus I9 dash R9 plus VEB17 plus R8 into here emitter current IE17 plus minus VEE. So this is the KVL equation. Now find out I9 dash, that is equal to, this one is cancel out, VBE17 plus IE17 R8 upon R9. Now here IE17 is equal to IC17 if base current, here we are considering this base current is nearly equal to 0. So if it is nearly equal to 0, so IE17 and is equal to IC17. So put here IE17 in place of this IC17. So we will get this equation I9 dash. Now here we have to find out current, collector current for this transistor Q16 and emitter current for this transistor Q16. So emitter current for transistor Q16 is how much? I9 dash plus this base current of transistor Q17. So here IE16 is equal to IB17 plus I9 dash. Now here IE16 is equal to IC17 if IB is nearly equal to 0. If we are considering here beta is nearly equal, very large, so that is equal to 0. But here we are considering that IC16, we are considering that here is some current. If we are considering here some current, so collector current upon beta, and if we are assuming it is 0, so you can put here 0. Now here we are assuming that IC17 upon beta is the base current across this transistor Q17 plus I9 dash. I9 dash, this equation you can put here. Now put here all these values. IC17 is known to you, 550 microampere, beta is 4 and NPN transistor is 200, VB17 is calculated 618 milliampere. It is calculated here. Now put, and R8 is given in the circuit diagram 100 ohm, R9 is given in the circuit diagram 50 kilo ohm. So put all these values in this equation and find out IC16. IC16 is 16.21 microampere. So here in this second stage also already calculated collector current and base current and emitter current in each of these transistors. Now moving for the next circuit diagram, output stage biasing. Now here in this circuit diagram you can see this, these two transistors are Q14 and Q20 are for output stage. Now here you can see this is also the circuit diagram. These are voltage drop across this transistor, this one and this one, दोनों का addition of these two voltage drop across this transistor Q18 and Q19 is equal to the voltage drop across this output stage. So we are, you can see this transistor Q13A is connected to transistor Q12, and it is in proportion. That means if we are calculating IC current, Q13A is equal to 0.25 I reference. Now I reference is also already calculated in the previous slide, and IC 13A is how much? 0.25 into I reference. It means IC 13A is equal to IE23 is 180 microampere. Now we are assuming that VB18, here in this circuit diagram we have to find out current, means this is total current, total input current across this circuit diagram, right? Now output current is also same, 0.25 I reference. So we should know the current across this circuit diagram, and we can calculate total minus this current and we will get this value. So we have to find out this current and this current and current across this transistor. So we know we are assuming VBE18 is equal to how much? VBE18 is equal to 0.6 volt. Let us assume this is VB18. So how much voltage is across this transistor is equal to this one. So VB18 we are assuming 0.6 volt is equal to current across this. Let us assume this is IC I10. So I10 is into R10 is equal to VEB18. So we can find out by using this equation, we can find out IE current across this R10 is equal to 15 microampere. If it is 15 microampere, so base current is nearly, this is diode connected transistor. So IE is equal to this one I10 is equal to 15 microampere. So this current is same flowing across this terminal collector current of Q19. So we can find out collector current of Q18. Collector current of Q18 is equal to this total current minus this collector current of Q19. So this is equal to 165 microampere. Now here VBE means, now here voltage, we have to find out voltage across this circuit diagram. So VBB is equal to VB19, voltage across this transistor 19 plus 18. So you can put this equation, VBEB is equal to VBE19 is equal to VT ln IC19 upon IS, and for this VBE18 means VT ln IC18 upon IS. So put all these values. IC19 you know 15 microampere, IC18 is 165 microampere, VT is 25 millivolt. Now saturation current for this transistor 19 and 18 is equal to 10 kΩ minus 14 ampere. Now you can put all these values in this equation and find out VB is equal to 1.118 volt. Now you know the voltage across this B to B point. So this voltage means across this circuit diagram, how much voltage is there is equal to voltage across these two transistors Q14 and Q20. Now VBB is equal to, you can write down this equation, VBB is equal to VT ln IC14 upon IS14 plus VT ln IC20 upon IS20. Now you can see, if we are assuming base current of this transistor Q14 and base current across this transistor Q20 is nearly equal to 0, so we can say collector current of Q14 is equal to emitter current of Q14 and collector current of Q20 is equal to emitter current of Q20. Now here it means IC14 is equal to IC20. So IC14 is equal to IC20. Now saturation current across this transistor Q14 and Q20 is equal, and it is equal to 3 times of the saturation current. It means 3 into 10 to the power minus 14. VB is already calculated 1.118. VT is 25 millivolt. Now we can find out, when we will put all these values in this equation, we can find out IC14 is equal to IC20 is equal to 154 microampere. So here in this output stage also all terminal current are calculated. So this is all about DC biasing of operational amplifier. So these are the DC collector current of this 741 IC. So Q1, these are the transistor Q1 to Q24, and already we have calculated collector current across this each transistor of this internal structure of operational 741 IC. So this is the reference for this presentation, Microelectronic Circuit, Cedar Smith, 7th edition, Oxford 2017. Thank you.